Okay, so in our triangles example, we were able to use rounding to convert from logical coordinates into device coordinates. So we used for IX this math round, and for max XY, or for max Y, we used math round Y. In section 1.4, the author is showing an example where we can kind of run into trouble. For example, if we're trying to map from pixel coordinates 0 through 9 to logical coordinates 0 through 10, rounding isn't going to work. So we need to figure out some other way to do it. Because basically what's happening is the pixel width from here to here, this distance is about 1.1 logical coordinates. So what do we need to do about that? So we try to get a better method for conversion by using x over the pixel width, and that'll, and then we do a similar thing with height. So once we start doing that, though, we're talking about scaling, right? We're no longer in a one-to-one correspondence with logical coordinate length and device length. Okay, so we can really go with any scale, right? We don't have to go, 0 to 9, 0 to 10. This could be, 0 to 1,000 and 0 to 50 or whatever, right? But then we have to start concerning ourselves with how are we scaling width-wise and height-wise, right? And that becomes an issue because of the idea of aspect ratio, right? So when you're looking at like paint programs, you get this idea, see where it says maintain aspect ratio. If you maintain the aspect ratio and change the size, let me resize this, let's say by 50%, and I say OK. So then everything gets smaller, but it's everything's in proportion. So that would be actually isotropic mapping. Okay, and then if we said don't maintain the aspect ratio, and I changed my vertical aspect by 50%, but not my horizontal, it squeezes things. Okay, so another way to illustrate that is if we look at let me look at the isotropic one first, actually. Let's see. So in the isotropic mapping, what we do is we have a pixel size rather than a pixel width and a pixel height. Okay, and we calculate that pixel size by taking the max of the R width and R height, and for our conversion, we're just using pixel size everywhere. Okay, so basically what we're saying is we're going to use the same scale whether we're talking about x coordinates or y coordinates. So if I go in here and run this file, we get our picture here. That's why the diamond stays the same shape. And when we click in here, you can see all the logical coordinates. I wrote anisotropic version of that that says, okay, let's separate out pixel width and pixel height, and in our conversions we're going to have a separate pixel width and pixel height, based on different logical width and logical heights. And that comes out to look like this. So now where we don't have aspect ratio locked anymore, so we're just resizing with separate scales basically for width and height. So that, and this is an anisotropic example. So that's the main difference between isotropic and anisotropic.